Works. Nice. Bold strategy, Cotton. Okay. Tomorrow is your test. Where is your test?
On the NTC.
No. Please don't spread misinformation.
Wait, it's in this room, right?
No.
Wait, it's at all of church.
It is at the Sundance Chalet, or whatever they call it, at the Granite Peak ski area. Please stop.
It's on the far side of the parking lot.
Correct.
Bring a jacket. It's cold. It's freezing.
Yeah.
Correct.
It's beautiful. And it's
Tomorrow,
freezing in there.
your test is at the Granite Peak ski area, Sundance Chalet. You need to be there at 7:30. Your exam begins at 8 a.m. Please show up at 7:30. Okay? Yes, don't be that person. You want to be there early. Huh? You got it. So,
Before 7:30.
the calc test on Tuesday was apparently rather chilly. Bring an extra layer. You can, if you have a shirt underneath, you can take that off and be good to go. If it's too cold, then you got the extra layer and you can be comfortable. For tomorrow, no cell phones, no smartwatches, kind of like a normal test, right? You got to be cognizant of what you bring. Wood pencils, they do not let you use mechanical pencils. Black or blue ink is probably also something you maybe want to bring. You can do your free response in ink if you prefer. I think it's probably smart to still use pencil.
You need it for like a signature.
Sure, you might need a pen to sign some of the intro forms or whatever they give you. I don't know. But wood pencils, black or blue ink. You do not get anything else. Bring your calculator. Pretty much every calculator on the face of the planet's accepted, unless you have like a, cell phone for a calculator, which is not allowed. But the Inspires are perfectly allowed on the chemistry exam. You only get the calculator on the free response section. You do not get a calculator on the multiple choice section. Yeah, thank you.
Oh my God.
That's what I was waiting for.
The first class for someone.
So the test is 2 sections. The first section is a 60-question, 90-minute multiple choice test. You get a formula packet and a pencil. When you take that portion of the test, you are allowed to write all over the test booklet, and you absolutely should. You're going to need to work some things out to the side. Please, if you get to a hard question, circle it, come on back later. Do not waste 10 minutes on an early multiple choice question to end up kicking yourself later when you're on question 44 with 30 seconds left, right? You don't want that to happen. When you get to a really, really tough one, circle, come on back later, okay? Answer every single question. There is no benefit to not guessing. You should have 60 answers on your test answer key before you're done with that section. Guess. Again, a 25% chance on something you don't know is way better than leaving it blank and making that a 0% chance. You just might get lucky. And speaking of writing all over that packet, cross things off. The more you can eliminate answers, right? If you take that from 4 options to 3 options, you've upped your percentage to 33. If you can take it from 4 to 2, you've upped your percentage to 50-50. The more consistently you can put yourself in those situations, the better you're going to score. So even if you don't commit to an answer the first time you read that problem, if you've crossed some things off and you come back to it later, maybe you can get it right. Maybe you can, the more coin flips you give yourself, the better off you are. Okay? Yes, Sophie.
You said earlier that you can't rip off the packet.
Correct. The formula packet is not something you bring, right? If you've had it all year, but it's not something that you bring to the test. The formula sheets that you've used all year are printed in your test booklet. They are in the front of the test booklet, and you are not allowed to rip them out. Ask the proctor. If they know what they're doing, they'll say, no, you can't rip those out. If they do say you can, then quite well, maybe, but question it. Like, I don't think you're supposed to. You're not allowed to. But yes, the formula packet is in the front of your test booklet. Bring multiple utensils, like you would want to anyway, I'm assuming. Put one right where that part is in your test booklet, and be prepared to flip back and forward. Please use your formula packet. Please. There's so much good stuff in there.
If it's not as good of a challenge.
No. Challenge not accepted. Use your resource, please. The free response section is next. It is 7 questions, 1 hour and 45 minutes. The first 3 are long. The next 4 are short. I would recommend the same sort of strategy. If you read a free response question and you're like, I don't know, skip it. Again, you don't want to try to like waste time on an early one that you don't understand, only to come to the realization when you get to question 7, right? All of a sudden you read question 7 with 4 minutes left and you're like, oh my God, I know how to do this. And then you don't have enough time to finish it. That sucks. I don't want that to happen. Please understand that the order you approach either section in is irrelevant, right? If you want to be funny and go from 50 to 1 on the multiple choice, perfectly allowed. Knock yourself out. You can, I don't care. But you get my point, right? It's an open, you flip back and forth, you start where you start, you finish where you finish kind of a test. So don't let the numerical order of their questions dictate how you answer your questions, especially for free response. Again, you don't want to leave question 7 sitting there only to realize that it was something that you possibly could have answered, but you didn't give yourself enough time to do so. Okay? Tonight, go to bed. For the love of God, go to sleep. Okay? Tonight is not the night to be staying up late. You can do no help by staying up late tonight. You just can't. I don't care if you think you're doing good by cramming stuff late at night until 1 a.m. You're not doing yourself a favor. You're gonna score worse. Go to bed. Now, if you want to get a cram session in, honestly, I would go to bed at 8:30, wake up at 5 a.m.
That actually
is.
Because then you're awake. Studying when you're exhausted is going to do you nothing. Studying when you're awake, actually, you might learn something. If you feel like you want to cram, because that's kind of the pressure, right? Like a lot of people get that pre-test pressure, and they want to like just cram and cram and cram. Don't do that tonight. Honestly, it sounds weird, but I strongly recommend going to bed at a decent hour, waking up early, and doing it then. That's probably a better choice. I'm not saying waking up early is fun. If you choose to do that, you're a brave soul. But I please, if you find yourself up late tonight and you're still looking at stuff, please go to bed. Please.
I read this like study that said that if you cram late at night, you're like 50% more likely to fail. It's like,
Lack of sleep is not a great state of like physical being to be in. Lack of sleep does not do you good.
that is their-
Because you need to go to bed early. Okay, so
The doctors say, you know,
who said that?
the doctors.
Who are the doctors?
They
Capital D on doctor too.
Anyway, so again, these are my tips. These are my advice. We're in the last 24 hours of the situation here. I want you to do well. I hope you're going to do well. Please hang out after school if you want to hang out after school. I've got a few takers already on that. Yeah, I'll chill here. Yep.
I'm not gonna do anything.
I don't care.
Okay.
I'm here to help you after school. Please feel free to take me up on that. And yeah, I think that's all I got for right now. Any questions? Anything else? Logistical questions from anyone? You know where you're going. You know what time to be there. You know what to expect in terms of length and questions and resources. Dylan?
So you said if we should probably get up early. What time do
do you get up?
Every day,
Yeah, what time did you get up this morning?
I was up at 5:45.
How? Same. Responsible.
But that's when I get up. I don't know. That's just when I get up. I don't know. Sorry. Thank you. I don't know. Okay, so let me rip through some things. I've got some Unit 4 stuff I want to talk about. I've got some Unit 5 stuff I want to talk about. I'm going to kind of skip Unit 6 because it's honestly thermodynamic stuff, and it was the easy thermodynamic stuff compared to Unit 9. So I'm going to hit 4, 5, and 7 today.
What about
Let's start in Unit 4.
Did you take AP Chem in high school?
It was not offered, but I would have. I would have loved it. I took advanced chemistry, which was my high school's version of like
Where did you go to high school?
Everest.
Ever.
I know.
Chemistry's pretty bad too.
Dude, it's awful. I've seen it. It's literally just basic chemistry. They're not even halfway through like where it's so sad. They're like learning how to balance formulas stuff.
That's tough.
I still don't know how to do that.
Me either. Okay, so let's talk about net ionic equations first today. Net ionic equations are when you dissociate any strong species. Now, there are 3 categories of strong species that we have talked about this year. They are strong acids, strong bases, and strong electrolytes.
Oh my gosh, really?
Yes, which more often, instead of calling them electrolytes, I call them salts. Salts that dissolve in water dissociate. Salts that dissolve in water are strong electrolytes, which means they are broken apart. So when it comes to net ionic equations, to determine how to write out a net ionic equation for any reaction, you've got to think about whether things are strong or weak. If it's a strong substance, aka strong acid, strong base, or salt, you break it apart. If it's a weak substance, it stays together. So here's an example. This is not an acid-base reaction, because I think those are the ones you're familiar with. I think those are the ones you're comfortable with. This is a precipitation reaction. Lead 2 nitrate. What kind of molecule is that, or what classification of chemical would that be? Lead 2 nitrate. What classification of chemical would that be? It's a salt. It's aqueous because it said it was aqueous. Yeah, I've got a metal and I've got a polyatomic ion. It's ionic, it's salt. So if I were to write out lead 2 nitrate and it was aqueous, how would I write that out in a net ionic equation? It needs to be dissociated. I've got to break it apart into its ions. It's a strong substance, okay? So I guess I'll write in B. I'll have lead 2 plus aqueous plus 2 nitrate aqueous. Now this ratio is based off of the charges, right? What's the other compound I'm reacting it with? Potassium carbonate. What classification of chemical is that? Salt. I've got a metal and I've got a polyatomic ion. It's ionic, it's salt, and it's aqueous. So what should I write it as? Dissociated. I have potassium ions, 2 of them specifically, and I've got a carbonate ion. Now, I'm being meaner here than AP would be. They would probably give you those formulas, okay? They're not really testing you on like names to formulas, formulas to names like we did last year. So don't worry about that too much. I know this looks maybe scarier, but they would give you those formulas, I promise. So they're both salt, they're both aqueous. I break them both apart. Now this question is asking me what makes the precipitate. There are 4 ions that no matter what they are with will always be aqueous. There are 4 ions that no matter what they are paired with are aqueous 100% of the time. Those 4 ions are ammonium, sodium, potassium, and nitrate. Whenever you see these four, they are aqueous. They will never, ever, 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 ever be your solid precipitate. Okay? Be on the lookout for these four. This is the aqueous stuff. So here's my reaction. I've got lead nitrate, potassium carbonate. What's going to be my possible precipitate? The lead carbonate, because the other option is potassium nitrate, but that contains two of these, so it's definitely not going to be a precipitate. My precipitate is going to be the lead carbonate. What happens to the potassium and the nitrate? They're spectator ions. In theory, I guess we would try to maybe put them together, but potassium nitrate is salt, and we're still aqueous. So how should we write it? Dissociated. So what do I have? I have potassium ions, and I have nitrate ions. So overall then, I can cross some things off. I've got some spectators. I have two nitrates, I have two nitrates. I have two potassiums, I have two potassiums. Neither of those ions did a darn thing. Those are my spectators. And my overall net ionic equation would be this. Okay? Be on the lookout for those strong substances. Again, the strong substances are one of three things: strong acid, strong base, or salt. Salts dissociate when they are in water, when they're aqueous. Jacob.
So if this was like a question on the FRQ, would we have to put absolutely every detail, or like?
No, if they ask for the net ionic on an FRQ, a free response question, go right here. If you're comfortable getting right to here, go for it. You don't have to show intermediate steps.
Okay.
Dylan. Yep, perfectly fine. I'm going to skip this. I'm going to skip a lot of 4, by the way. Yep. Yep. Let's do a redox. Oxidation numbers. For oxidation numbers, you've got some rules. If any element is all by itself, it has a 0 oxidation number. That includes diatomics. If I have O2, H2, N2, those all have oxidation numbers of 0. The other rule, or the next rule, is any ion all by itself has an oxidation number equal to its charge. So the oxidation number of chromium here is 3+. Oxygen will generally be 2-. Hydrogen will generally be 1+. And all of the other elements, we've got to math out. We've got to figure it out. Let's start here. I've got 4+ -2 for a grand total of 2+ so far. And I need this molecule to be neutral in total, right? So what do my carbons need to equal in order to achieve that? I currently have 2 positive on this side. What do these need to equal in order to get me to 0? 1- individually, right? 2- total, but I've got 2 of them. So individually, my carbons are 1- here. In this molecule, I have 6+ -2. I need this to be neutral once more. I currently have 4 positive total, which means I need my carbons to equal 4 negative total, but I have 2 of them. So individually, they are each 2-, or 2-, sorry. Could have taken the test tomorrow. You would have done well. Over here, I have 14 negative with the oxygens. My total needs to be -2. So I need my chromiums to equal 12 positive total. I've got 2 of them. So individually, they equal 6 positive. When you write in oxidation numbers, it is on an individual basis, right? You really should not write in 14- up here. That's the total, but the oxygens are 2 minus. You really should not write in 6 plus right here. That's the total, but hydrogen is 1 plus individually. The oxidation number is on an individual atom basis, not on a total basis, okay? So what was oxidized, what was reduced? You want to look for reduction. I'm going to fall. Reduction is way easier because that's the number that goes down. What went down? Carbon did. -1, -2. We gained 1 electron. What went up? Chromium. There it is. Oxidation, lose 3 electrons. Okay, let's take our 2 halves, pull them down, and balance them individually. The oxidation half is going to look like this. The reduction half is going to look like this. And now we start the balancing process. The first thing you want to balance is elements other than oxygen and hydrogen. Up here, I have 2 chromiums, I have 1 chromium. That's an issue. There we go. Down here, I've got 2 carbons and 2 carbons. Okay, we're good there. After the non-hydrogens and oxygens are balanced, we go to oxygen next. I've got 7. I need to fix that by adding water. I add water. Down here, I've got 4 and I've got 6. I'm doing it the same way. I've got to add water to balance those out. I'm sorry, what am I doing? Sorry. Bad teaching. Nothing. I got 1 and I got 1. I was looking at hydrogen for a second. My bad. Going too fast. So now we're good with oxygen. Let's go to hydrogen. I have 14. I need 14. I fix that by adding H1 plus. I've got 6. I've got 4. I fix that by adding H1 plus. Now I've got to do the electrons. To get the electrons, we look at the charge on the reactant side and the product side. This reactant side has a total charge of 6 plus, right? 2 times 3. This product side has a total charge of 12 plus. I need my sides to be equal. So I need to bring down the 12 positive until it equals the 6 positive. I do that by adding 6 electrons. Down here, this side is neutral, this side is 2 plus. I need to bring the more positive side down by adding electrons until it equals the other side. The very last step of balancing redox involves making sure however many electrons I lose matches how many electrons I gain. I'm losing 6, I'm gaining 2. Those don't match. So I'm going to multiply the bottom half reaction here by 3 so that I lose and gain the same number of electrons. I can then transfer my information to the overall balanced reaction. Water, I've got 7. That's it. 7 waters. Hydrogen ions. I have 14 on this side. I have 6 on this side. They cancel out. And I have 8 remaining on the product side. And then I transfer up all my coefficients of everything else, right? So I have 2 of these, 1 of those, 3 of these, 3 of those. There are a couple of really annoying exceptions that have shown up on the AP practice tests. Okay, if you've been doing a lot of practice material, you've probably come across at least one of these examples. There are 2 redox reactions in the practice tests that involve exceptions. And I really hope they don't do this to you tomorrow, but I'm going to try my best to say it now and maybe it'll stick in, 20 hours. I hope they don't do it to you. The 2 exceptions that they have shown in the practice tests are this, hydrogen peroxide, and this, Lithium hydride. Over here, the hydrogen is going to be what you always thought it was. But in order for this to be neutral, the oxygen has to be 1 minus. In peroxides, these are called peroxides when it's like something to O2. In peroxides, oxygen has a -1 oxidation number. Very obnoxious. Over here, this is called lithium hydride. This, when hydrogen is listed second, it's negatively charged. And it's called a hydride. Lithium would take on its normal common charge, the one you would expect it to be. But the hydrogen is going to be the opposite of what you would expect it to be and be 1 negative. These are 2 exceptions they have used in a couple of those practice exams. I hate when they do this because then it's like, it's hardly testing your redox knowledge. It's testing like, hey, did your teacher teach you that one random side note that never shows up? Oh, they didn't? Oh, you got the point wrong. Like, so frustrating as a teacher. Dylan.
So in like, for instance, peroxide example, are they ever going to change the H with like a K?
Yep.
It could be K2O2.
Yep.
And for the lithium, it could be something.
Some other metal. Yep. It could be NaH, KH. Yep.
Basically, we should just remember the form.
Yeah, it's the, yes, correct. It's more about the form than it is about the specific examples I've used. Go ahead, Jack. What were you complaining about?
Anything to say?
Sounded like you were complaining about my teaching.
No. I just said I'll take the point off.
Oh,
Wait, can you do, what if you put a 2 minus as well?
Because then it doesn't
Then
balance
H
out.
is not one.
then hydrogen would have to be 2+.
What's not?
And if you know anything about hydrogen, yeah, hydrogen's more rigid.
So oxygen can be different?
Yeah, oxygen's got a little more flexibility with its electrons.
Is lithium the one that we talked about earlier, Near, or is that beryllium? The one that was, there was another special.
Oh, yeah.
Beryllium hydroxide is a weak base. So like the first 2 columns of the hydroxide is always strong. Beryllium hydroxide is a weak base. But don't worry, that one they don't use. I'm positive.
Sure.
Yes, that one is specifically listed in the gigantic 200-page document that I get to teach this course. That one is specifically listed that they will never use it. I wish they would do the same with this kind of crap,
Yeah.
but for whatever reason, apparently oxidation numbers aren't under that umbrella. No, I will not calm down.
We should start a petition.
Yeah.
I'm about to break something. Let's go to Unit 5.
We're fired up in here. So why are we doing this?
Why aren't we doing Unit 6?
It's okay.
'Cause I think it's actually kind of one of the easier ones.
Wait, what is this?
Like the thermodynamics, but
6 is the first unit of thermodynamics, but it was the easier of the 2.
I think that's the one test that I took and was like, did really bad.
6?
No, I hated it.
Oh, what?
It was one night.
Half-life.
That I slipped
If
away.
you see anything about half-life anywhere, it is first order. Every single time.
Why did you teach us the other order?
Because it's not always about half-life. But if half-life shows up, if they ask about a half-life, if they give you a half-life, if there's a graph about half-life, if there's data about half-life, spoiler alert, what they have provided you is a first order reaction every single time. Guaranteed. Yes, correct.
Or like
Yes.
every single graph always comes
Now, almost all half-lives are first order, but AP only uses its first order. Yes. So when it comes to half-life, we've got half of our quantity going away. And a half-life is a length of time. How long did that take? So in this instance, it took 35 years. When half-life is first order, which again, for us, it always is, the half-life is constant. It will never change. Every single time that we cut it in half will be the same length of time. In other words, I went from 1,000 to 500, it took 35 years. I'm gonna go from 500 to 250, and it took 35 years. And if I went from 250 to 125, it's going to take 35 years. Okay? So, if you see half-life, it is first order, and the half-life is constant. It's not going to change. Now, that's also an indication. Sometimes they're like, you know, here's some half-life data. What's the order of the reaction? And you should say something along the lines of, based on the fact that the half-life is constant, that's representative of a first-order process. Okay. You may. You also have an equation for half-life. It's in your packet. T1 half equals 0.693 divided by K. Sometimes they might give you a half-life and ask you to solve for the rate constant, little k. Other times they might give you the rate constant and have you solve for the half-life. You plug in little k, you solve for T1 half. It's in your packet. It's pretty easy if it comes up. You just got to be able to find it and make sure you're picking the right thing, right? Let's do this. This is the method of initial rates. This is determining a rate law from a data table. From trial 1 to trial 2, my molarity of CH3 CBr has doubled. My molarity of hydroxide was held constant. This molarity doubled. Without even thinking, I should know that my rate needs to undergo that exact same change raised to a power. What's the power of my change over there? 2 squared, because this quadrupled, right? And again, the scientific notation stuff gets a little obnoxious, but hopefully this can make sense. 4 times 4 is 16. There's 1.6, and what have I done? I've shifted the decimal 1 place over. So this is a quadrupling. Even if they give you these types of numbers in the multiple choice section, you should be able to do that mental math. Okay? So this is 2 squared. What that means is this reactant is second order. Let's look at the other reactant. I need 2 trials where this is held constant and this changes. So let's use trial 1 and trial 3. Trial 1 to trial 3, this reactant is constant. This one doubled. Without even thinking, I know my rate must undergo that same change raised to a power. What power am I going to raise it to this time? First. So overall, what I have is that rate equals K multiplied by this reactant squared multiplied by the other reactant to the first. That's my rate law. This is called the differential rate law, or I sometimes call it like the normal rate law. Rate equals K multiplied by reactants raised to the power of their order. This is not in your formula packet. They won't make you do math with this, but they sometimes like to use this. They'll give it to you sometimes. They'll reference it sometimes, but you'll never have to plug numbers into it. Okay? In your packet, you have 3 equations, well, 4 equations for kinetics, but 3 related to the order of a reaction. The first one listed in your packet is 0 order. That's like the concentration at time t minus the concentration at time 0 equals negative kT. The second one is first order. That's the natural log one. The third one is second order. That's 1 divided by the molarity. Those are the 3 kinetics equations that you may have to use and do some math with. Let's practice that right here. NaOCl is a corrosive reddish yellow gas. It follows a second order rate law. Rate equals K times NaOCl squared. They told me the order. Okay, good. The rate constant is 0.025. The initial concentration of NaOCl is 0.400. What will the concentration be after 1200 seconds? What equation do I want to use? 1 over, because that's the second order equation. That's I got to pick the right one. I have 1 over my concentration at time t minus 1 over my concentration at time 0 equals K. What's K? Multiplied by T. What's T? You got to pick the right equation based off of the order. You got to plug everything into the right spot, and then it's algebra. First order calculations are probably the toughest because that's the one that involves the natural log. So sometimes you have to get rid of that natural log, right? Which means like e to the power of both sides when it comes to that. Oh.
Did you put 1200 in the T in the equation like at the beginning with the low T, the 1 over concentration?
Yeah, so yes, okay, so this is just like an indication of when it happens, right? So when I say molarity at time t, the t is quite literally the same. So we could, if you wrote like subscript 1200, yeah, it's not mathematically going to change anything, right? Because we don't acknowledge that number, but it is telling me exactly when that occurs, yes. And this is always written as like that at time 0, right? Subscript 0 implying initial. You plug all this in. What do you get? Did anyone do that? That's what they told me last hour.
You trust it?
I think so. Just trying to streamline the process here. I want to get through as much as I can. So when it comes to math and it comes to kinetics, figure out the order, use the right equation. The first one listed is 0, second one listed is first, third one listed is second. 0, 1, 2. The half-life equation listed at the bottom of that section of your equations is for first order reactions, because half-life is always going to be a first order question. How we doing? In order for a reaction to occur, molecules must collide in the correct orientation and with enough energy. This is known as the collision theory of chemical reactions. Basically, reactions happen when molecules hit, when they collide. But that collision needs to meet 2 criteria. The first, they need to hit with enough energy. The second, they need to hit in the correct way in order to actually make the products. Okay? This does come up. This question will come up most likely tomorrow somewhere. Okay? The collision theory of chemical reactions generally does make an appearance. And again, it's the 2 criteria. Well, I guess it's kind of 3. 1, they need to collide. 2, they need to hit with enough energy. 3, that needs to be in the correct way or the correct orientation. I think we're good here. Endo or exo? Exo, why? There's my start. There's my finish. I've lost energy throughout the process. Energy is being released. That's exothermic. Okay. What's a catalyst? Catalyst speeds up a reaction but is not used up. Correct. It lowers the activation energy. Speaking of which, here's our reaction energy profile again. Reactants, products. Here's the activation energy. The height of the peak is the activation energy, if you remember. The higher the activation energy, the slower the reaction. The smaller the activation energy, the faster the reaction. When I add a catalyst to speed it up, I'm literally lowering the activation energy. I'm giving the reaction a different pathway that requires less energy. This will stay the same. This will stay the same. But the path I take will require less energy. That's what a catalyst does, okay? Reactants, products, activation energy, change in energy. Again, this example is showing us an exothermic process because where I started and where I ended, I have lost energy. This would be delta E, and delta E would be negative. Delta E is positive. That's endothermic. Make sense, right? That's hopefully pretty familiar, I hope. What two criteria must be met in order for a proposed mechanism to be acceptable? In order for a mechanism to be acceptable, the little steps, the elementary steps, must add up to the overall reaction. That makes sense. That feels very logical. And the slow step must match the rate law. We're going to talk about that one because this generally shows up too. Okay. Now, what's really, really important is that you understand that a mechanism is elementary steps, meaning I have multiple individual steps that when added together, give me the whole reaction, give me the whole process. When we analyze those individual little steps, the elementary ones, the slow one is the one we're interested in. It's also sometimes called the rate determining step. The rate determining step is the slow step. It's the one that determines the rate. Sorry for the circular argument, but that's the truth. Okay, so let's look at this example. I'm going to go quick. I'm going to give us the rate law just really, really fast because I don't really care about the data table in this one. I care more about the other part that I was just telling you. So from trial 1 and 2, this doubles, that quadruples, so it looks like B is second order. From trial 2 and 3, this doubles, that doubles, so it looks like A is first order. Okay, so my rate law would look like this. All right, I don't really, that's not my concern right now. I just need that to explain the other part. Part of a mechanism being a good mechanism means that the slow step matches the rate law. The reactants of the slow step must match the rate law. If the reactants of a slow step do not match the rate law, the mechanism is not a good mechanism. So off of that basis, of the 4 mechanisms that are proposed for this example, the only one that could possibly work is number 2. Because this slow step has reactants that match the data, that match the rate law. I have 1A, A to the first. I have 2 B's, B to the second. They're either going to give you this question in one of 2 ways. They're either going to be like, hey, here is a slow step. What's the rate law? And then they'll give you 4 rate laws to pick from. Or they're going to be like, hey, here's the rate law. Which of these is the slow step? And all you're trying to do is match the reactants of the slow step to the rate law proposed. Cool.
Intermediates don't change, like,
When you have an intermediate,
it wouldn't change if I get canceled out one of the things in the slow step, like the reaction.
if you have an intermediate, you would need to like trace it back to the previous steps, to the previous step, and use the reactants of the previous step in place of the intermediate. They generally don't do that. I have not seen.
On one of the practice ones, like they cancel out.
That was a catalyst,
Oh, okay.
and they included the catalyst in the rate law. Yes, and that should be there.
Yeah. That one that they counted.
Yes,
Okay.
I know which one you're talking about. Chlorine, right?
Yeah, I think so.
If they give you data and they give you graphs on kinetics, what are you looking for? The linear one. We want to find the linear plot. When you find the linear plot, look at the axes. The axes will tell you what order you have. In this instance, our linear plot is the natural log of concentration versus time. That must mean that we have a first order reaction. We make 3 graphs with kinetics. We have concentration versus time, natural log of concentration versus time, 1 divided by concentration versus time. Those look awfully similar to the 3 equations in your packet. If concentration versus time is linear, you have a 0 order reaction. If natural log of concentration versus time is linear, you have a first order reaction. And if 1 over concentration versus time is linear, you have a second order reaction. So looking at the graphs that I have for this problem, what order is this?
First order.
It's got to be first, because the natural log one is the linear one. Okay, knowing that, I get this differential rate law. Rate equals K times the molarity of the reactant to the first power. And what integrated rate law must I use? I must use the one that's first order from my packet, which is the natural log one. Part C is asking us for the rate constant. There's a couple different ways that this might show up. They might just make you plug in numbers, meaning I would use this equation, I would plug in what I have, what I know, and solve for K. Works, totally fine. However, what's also true is that the slope of the linear graph equals the rate constant. The slope of the linear graph equals little k, the rate constant. The slope of the linear graph equals the rate constant. The slope
Can you write it down?
of the linear graph equals the rate constant. So if you need to solve for k, that's why I said it 4 times. Well, cool. If they give you the slope of your linear graph and they say, hey, what's the value of k? You don't have to solve a darn thing. It's the slope. K equals the slope. The rate constant equals the slope. I don't know if that's going to show up, but if it does, it's going to save you a ton of time. Because if they give you like a linear equation for this, right? And they ask for you to solve for k, they've already done it for you. There's nothing to do. You just take the value of the slope. So that may or may not, it's happened before. I've seen it before. Just a side note. All right, let's go to unit 7. I don't got a ton of time, but we're going to try. I believe in you. Do I have unit 7 open? There it is.
The other K.
Unit 7 is equilibrium. Unit 7 is ice table-tastic.
Unit 8 in the mod table.
Yeah, unit 8 is when we introduce neutralization, yes, and acids and bases. Now, unit 7, there's all sorts of different K values, right? This year, we have had Ka, Kb, Kc, Kp, Ksp, Kw.
I like Q better.
When I say K subscript C, what does that mean?
Polarity.
Concentration. It's redundant. It's redundant. Because when we set up the value of K, we're almost always using concentration. Don't let that throw you off. Let's solve number 2. Now, in this one, we have an equilibrium involving gases. And they're telling me that I have an initial pressure of 2 atmospheres of my reactant gas. This is going to be a KP problem. The reason why I wanted to go through this one is because when you solve for KP, you're not using molarity. You're using partial pressures. So, setting this up, I will need an ice table. I'll need 2.0 for my reactants, 0 and 0 for my product. And then we're going to see if what this thing does when it reaches equilibrium, right? So here you go. I'm just going to scroll down and show you everything. Trying to save myself some time from last hour. Sorry about that. It's kind of a wall of info, but let me walk through it. I set up the ice table. Again, I initially have 2 atmospheres, none and none. I know this is going to go down. I know those are going to go up. I set this up. I have my equilibrium. When you're done with an ice table, what's the very next thing you always do? Set up K. Solve for K. When I set up K, don't mind that. When I solve for K, I set it up as products over reactants. Products over reactants. And when I do so, when I do so, I either use molarities. Most of the time I use molarities. When I do that, I use brackets, right? But with KP, it's unique. We're not using molarities, we're using pressures. So I need to write that appropriately. If you use brackets in a KP problem, you're going to get it wrong because you're not using molarity. You're using pressure. So I need to write it out this way. Partial pressure of that product, partial pressure of this product, divided by the partial pressure of that reactant. I plug in what I know. They gave me a value of K. I ignore the change in X. I do the algebra and I solve for the partial pressure at equilibrium. They wanted the partial pressure of everything. I didn't write that out. But I would have this equals 3.26 times 10 to the negative 3 atmospheres. This equals 3.26 times 10 to the negative 3 atmospheres. And this equals 2 minus that, which is really just going to be 2 with sig figs. Okay? So that one's unique because it's pressure. Let's go to KSP. Because KSP is also unique. With every KSP problem, the reaction gets set up as solid reactant, aqueous products. Every single solubility equilibrium constant, the reaction is solid salt as the reactant, aqueous dissociated ions as the product. Okay? In this one, they have given me the molar solubility. Fancy words. What does that mean? It's the molarity of how much of that stuff dissolves. Sometimes they ask you to solve for molar solubility. Don't freak out. They just want the molarity of what dissolved. That's all they want. So in this one, we have an initial molarity of that salt. Here's my question to you. I know how much dissolved, how much of it breaks apart. 100%. Why? Because it's salt. What do salts do when they're in aqueous solutions? Dissociate 100%. It's one of our 3 strong species: strong acid, strong base, and salt. Does this dissolve well? No, not well at all. The molarity is 4.52 times 10 to the negative 5. That's ridiculously small. But even though a tiny little bit dissolved, 100% of it dissociates into its ions. Whatever tiny little portion dissolves, 100% of it breaks apart. Do you remember that talk when I said that like every single day for like a week? It doesn't matter how much dissolves, 100% of it breaks apart. That was my catchphrase for a while. Not a great catchphrase, but you definitely heard that this year. Much like the slope of a linear kinetics graph is equal to the rate constant. Trying it out, seeing how it fits.
Well, next year students have to do the experiment seminar.
The lab?
Yeah.
Yeah, it'd be great. They're gonna have fun. It adds a whole other dynamic to this class.
Struggling for 2 hours every Friday.
Yes, struggling for 2 hours every Friday / doing a lab notebook every Friday. You guys would have hated it.
Yeah.
Yeah.
I thought you said it wasn't that
Well, it's not bad when he does it because it's a 20-30 minute video.
I enjoy it. It's kind of fun.
Suffer for 2 hours. but-
Exactly. No, that's because he's a chemistry nerd.
That's true. So here's the setup.
I have the following announcement. When Nicholas gives, please report to the main office for his
Oh my God.
Oh my God.
In addition, seniors.
Wonder if he's negative or positive.
Graduation ceremony will be available beginning
If he's going to the office, probably negative.
at 8 a.m.
Just go down.
Thermodynamically favorable.
Available to seniors.
Wonder what his cell potential would be. I don't know. Sorry. Okay, so in this one, I know 100% of it breaks apart, right? On the product side, how much do I get? Be careful with your coefficients. 1, 2. This goes up by x. This goes up by 2x. That's my value of x. So when I plug in KSP, by the way, it's still set up as products over reactants, right? It's just that my products are aqueous and my reactant is solid, so I don't include it. So it's literally just products over 1. I plug in the molarity here. I plug in the molarity there. Now, this gets doubled, and then it gets squared because of the way that gets established. I don't know what KSP is. We didn't plug it in last hour, but that's the setup. Please, I beg of you, tomorrow, again, please go to bed at a decent hour tonight. Do not stay up late studying. You are not helping yourself. You're not. If you feel the urge to cram last-minute chem knowledge, do it tomorrow morning. That's not fun either, but it's gonna be more beneficial to you. Your brain works better on rest. Trying to study late at night is not good.
Don't do that.
Oh, yeah, no,
I don't even know what.
Feel free to hang out after school. I'll be chilling as long as you guys need me.
Yeah.
Have a lovely day. Best of luck tomorrow. I believe in you. You can do this. You can do this.
This is 2018.
Good luck, guys. Good luck.
Sophie, you talked to Spencer. I'm here for an hour. About my stuff.
Okay, it's like-
Yeah, I know. Because I just didn't know if you had.
Yeah.